the previous days, we have made a general introduction to the topic of control, addressing some traditional motivations coming often from science and technology and industry. We have also established some of the fundamental ideas in calculus of variation, optimization, and control. And we have also seen the very tight link with the modern theory of machine learning that, as I was showing you the last day, is very much based on an intelligent combination of all the tools developed in these fields, in particular in control theory, but with a different kind of application in mind, in which often we are not dealing with the classical systems of mechanics like the pendulum or the Navier-Stokes equations, but rather with simply the necessity of understanding data, big data, a big amount of information that we receive nowadays in many contexts, and that we have to handle, we have to manipulate to extract relevant information and improve processes, as could simply be communication online, for instance, right? Okay, so then, as we have shown, whenever you address these topics, also in machine learning, it is to you to decide what kind of modeling you are going to employ. The same happens when addressing the problems of nature, of technology, of industry. For the same problem, there are very many different degrees of complexity on the models you consider. And of course, you have always to take into account this Occam reservoir principle in the foundations, in the philosophy of science, that indicate that very often the best possible model for a given process, for a given system, is not the one necessarily that is more complicated, the one that is integrating all possible tiny details. Because if you put all these details together, the model might risk to become so big, so complex, that afterwards, when you will have to face issues such as numerical simulation, control, parameter identification, optimization, and so on, the model will simply be too big, right? And you will face the course of dimensionality. While very often, we are interested on some very specific features. For instance, in the first example I gave, the work that Lord Maxwell did back in 1868, where he was trying to understand the stability of the governor, the rotating ball mechanism that was able to stabilize, pressure within the steam engine. He didn't consider the most possible sophisticated model. He took the simple harmonic oscillator with damping, and we saw already on this second order differential equation, by computing the roots of the characteristic polynomial, we understood that the decay properties of that system are not monotonic with respect to the parameters, right? And this was the key observation that explained why the technicians, the engineers that were trying to tune, right, these mechanisms, sometimes they were failing on doing it properly. Why? Because they were looking for perfection. They were increasing the parameters of damping, while eventually, as we have seen, the decay rate of a system, whenever it is second order in time, is not monotonic, right? It's monotonic for small variations of the parameters according to intuition, right? If you press harder, the response will be better. But eventually, this simple intuition breaks down, the process saturates, and once you keep increasing the damping, the velocity of propagation starts to degenerate, to decay, right? So then that was a warning. All this together makes that when you are dealing with control systems, before you get into very sophisticated system, it is much better to first analyze the issues from a simple modeling perspective. So you first adopt a simple modeling paradigm where the analysis will be much faster. You will get a better understanding. You will be able to do numerical simulations much faster. And only after you realize that the conclusions of this process are correct, you can proceed to the next step and analyze how you enrich your model to get some further, detail, right? So it's the principle of the zoom, right? So you don't try to get the global picture from the very beginning. So first you look to, you observe the process from a given distance. You try to get an understanding of the global picture. And once you have, understood the global landscape of the process you are considering, you zoom in order to gain knowledge about details. This is why it is natural in the control of processes from a mathematical perspective to proceed in an iterative manner, adopting first the simplest models to then increase the complexity of the models to gain detail, right? Okay, so what is then the simplest model possible? Is the finite-dimensional system that we already discussed the other day, right? Very briefly. And today in this first class, I would like to, work out a little bit the details of that system because it's really central in the theory. Here you see already some of the key features of control theory that once you understand in this very simple linear deterministic finite dimensional paradigm. So this is linear, right? It's linear because, the ODE under consideration, right, is linear. The control is entering linearly as an additive force. So it's finite dimensional, right? Because we are just working in the Euclidean space, right? So we are in dimensions n, right? We are not working in an infinite dimensional Banach space. The problem is also, the model is also deterministic, right? So I didn't add any noise to the system, right? Of course, you could always argue that the nature is more complex, that there is always noise, there are always uncertainties that you cannot really anticipate. You could also argue that oftentimes the models in mechanics are nonlinear, right? There are nonlinearities involved, like in the nonlinear pendulum or the Navier-Stokes equation. You could also argue that in many applications, the state is really an infinite dimensional variable, not necessarily a finite dimensional one. This is true. But as I said the other day, when you are looking, for instance, to the propagation of heat, right, in a building, right, where you have a finite number of offices, you could adopt the point of view of a very complicated heat equation in a three-dimensional domain, right, occupied by this building. But it is very legitimate also and very practical to simply think, okay, let me, rather than doing the heat equation on a complicated domain, let me just, consider the different offices in this building. Let me, measure temperature in each office through a thermostat, and let me just, build a state which is just considering the temperature given by the thermostat, the average temperature in each of these offices, right? So in this way, I will have a finite dimensional system in which the state X, I will not denote it by a vector, but I mean, just to simplify the notation, but it's of course a vector, is a vector of n components, right? Each of them representing one of the projections of the state into one of the n canonical directions of the space, right? So then in this finite dimensional system, n is the number of components of the state, right? So x is a vector with components x1, xn. These components are evolving in time. This is something we observe normally in nature. There are phenomena that are purely static, right? So if I look to the wall in my office, I see nothing moving, right? So it's basically a static. Of course, if I will consider a very long time window, I will observe that indeed, you know, there is some elasticity on Earth. This is motivating some mild bending on the walls, but this will take years to observe, right? So the time scale is very, very long for these processes. So if I just watch the wall of my office, I see a static process. But when we are dealing with temperature, when we are dealing with traffic flow, when we are dealing with the flow of information in internet, when we are dealing with waves on the sea or wind in the sky, of course, there is a very obvious motion, and therefore the state has to be described as a vector function depending on time. Okay, good. So this is the state of the system. So this is the state. Right? So we say is the state is the quantity of interest, right? This is the variable I am interested on, right? Good. Now, in this system, A is a given matrix, right? So A is a matrix n times n. So what does the matrix n represent? It represents the free dynamics, right? What do I mean by free dynamics? I mean that if I was not acting on the system, if u were 0, right? If u is equal to 0, right? Then the solution xt will simply be exponential atx0, right? So this is the free dynamics. It's completely determined by the initial data. So this is the Cauchy problem, right? If I don't act on the system, if u is equal to 0, this is a classical linear Cauchy problem. And I know there is a unique solution that is fully determined by the initial datum, depending on the properties of the matrix A, the spectral decomposition. This solution might decay, might grow, maybe it oscillates faster or slower, but eventually the dynamics is fully determined. There is nothing to be done, just solving the Cauchy problem. As you know also, the linear theory for differential equations can then be extended to nonlinear theory using the variation of constant formula, the integral representation of the ODE, and the Cauchy-Lipschitz, contraction principle, Banach theorem. And if you are in an infinite dimensional setting, you can use the theory of semigroups to give a sense to the same formulation. Of course, in an infinite dimensional setting, you have to think a little bit more. What does it mean to write down the exponential of an operator, right? As we will see, the exponential of a matrix is an object that is easy to define. It's much harder in the infinite dimensional setting, and this is why you need semigroup theory. But if u is equal to 0, there is no control theory. There is just a state, free dynamics governed by the matrix A, right? And therefore, the only thing you can do is analyze the Cauchy problem, existence, uniqueness, and possibly maybe some issues about numerical approximation that, of course, you can handle by different methods to get different degrees of, say, efficiency on the approximation. You can use Euler methods, you can use Runge-Kutta methods, you can use multi-step methods, and so on, okay? But that's it. Now, the point in control theory is that we are definitely interested on controlling the system. So for us, the key is that the control U will be there, right? The control U will be there. Where's my pointer? The control U will be there. And then the control U, right, will be assumed, the control U, right, will be assumed to be of dimension M. So typically in applications, so the control U will be of dimension M. And typically in applications, M will be much smaller than N, right? In particular, in this example of an intelligent building, right? You expect to regulate the temperature, the flow, the intensity of all the air conditioning, so to regulate, right, intelligently, in an efficient manner with a low energy consumption. You expect to regulate the temperature in the ensemble of the offices of the building just by, from just one office in which automatically or through some, say, responsible person in charge, you will simply regulate temperature everywhere. And so typically, you will, of course, the ideal case, right, will be when you have just one control, M equal 1, right? Then if M equal 1, then the control U is just an scalar, is UT. And then with UT, when you say U large, you mean a lot of intensity, positive, negative. When U is small, you simply mean a small intensity, positive or negative. And when U is equal to 0, you mean just you stop the controlling engine. So you are just regulating the intensity of one control. So the ideal case will be when, when you have just one control, but the number of state components is huge. So you can aim to control a large dimensional system out of very few controls, okay? So this is the game to play. And then the question is, how do I formulate the control problem? Well, the control problem can be formulated as follows. You are given this system, typically in a time horizon, right? So, for instance, when you have to prepare an exam, you say, okay, exam is next Friday. So I have 1 week, I have 7 days. So T is equal to 7. And I have to organize myself out of the initial data where I am, right, to the final time horizon next Friday. I have the exam, right? And what is the goal? Well, the goal typically can be, written in the form of, right, trying to reach some given target at the final time. You are planning a trip and you say, okay, I would like to be tomorrow at noon. I have a lunch in Beijing, right? So then I have to organize my trip so that tomorrow at 12 at noon, I'm sitting in that restaurant when I meet my friends, right? There are many ways of organizing this trip. You can go by train, you can go by plane, you can go today and stay there overnight. You can travel tomorrow morning early and then do it in one shot, right? You can do it in many ways. You can take the metro once you get to the train station, or you can take a taxi. Okay, so there are many ways for doing this, but the goal is very clear. At the final time, you want the state to be xt. In this case of the officers, you say, well, our, company starts operating at 7 a.m. and therefore, independent of what the temperature was overnight, maybe it was very cold or very hot, independently of that, at 7 a.m., I want all the offices to be, 19 degrees, so that when workers get in, they feel comfortable and they feel motivated to work, intensively. So there is a time horizon for the control problem. So this is the time horizon, capital T, right? And there is a target, an objective. And the objective is to drive the solution to the final state. Of course, this is just an example, right? You could say, well, you know, today, for instance, I'm not interested on controlling the full state. I just interested on controlling some projections, right? So why? It could be that, you know, on weekends, people only use the first floor. There are fewer workers during the weekend, so people are just occupying the first, you know, floor in the building. Then I don't care about the temperature in the upper offices. I will not spend energy on regulating the temperature in the upper offices. I just do it in the first floor. So then you are not controlling the full state, you are just controlling some projection. Right? So this will be a kind of partial control or controllability problem, right? Or it could be, well, I'm not interested on controlling exactly. I will be happy if the norm of the difference is just less than epsilon. And this is how we typically work in practice, right? So when you get into your car and you regulate the temperature in the car, say, okay, 20 degrees for driving, well, I'm not sure the car is exactly 20 degrees, right? So maybe it's 20.1, right? Or 19.97, but we as humans, right? Our inner thermostat doesn't really make such a big difference, right? So for us, temperature nearly 20 is fine, okay? So in many practical applications, this kind of approximate control problem or this kind of partial projection control problems is sufficient, right? Okay, so then what are the other ingredients of the control process? So one, as I said before, is the matrix A. So the matrix A is the matrix giving you the dynamics of the system, right? There is nothing you can do about it. A is determined a priori, right? In the sense that, for instance, A will be how, you know, the different offices on the building are interconnected, and therefore how the temperature in one room is, say, affecting the temperature in the neighboring rooms. So typically, capital A is a matrix that is related to the geometry of the configuration you are considering and the connectivity between the different components. So for instance, if I am considering this building, I see that this, you know, this office here in the front on the basement is very far from the opposite, for the office that is in the opposite corner, back in the upper floor. So probably the coefficient Aij corresponding to the office I and J, offices I and J, the connection between these two is so weak that this coefficient will simply be zero. But whenever I am considering offices that are adjacent, I know that a very hot temperature in this office will end up influencing the office next to it. So then the coefficient on the communication of these two in the matrix A, on the connectivity matrix A, will be non-zero. Okay, but this matrix is given. Okay, and now B is a very significant part of the control process, because although the A is given, right, the A is the way it is. So you go to a city, you go to Beijing, and A represents the roads, the streets. You cannot change the streets. I mean, you can do it in a longer time horizon, but not when you really face the problem of regulating traffic. But you can decide B often, right? So B will be, where are the actuators located? So where are the intersections in which we'll place policemen that will regulate traffic? Or B will represent where the red lights are collocated, how many red lights you need, and where are they placed, right? And you see, this is often a very interesting problem. You are walking a very long avenue, you are a pedestrian and you want to cross the avenue, and you know that very often you cannot do it in any place. You have to, look for a pedestrian crossing path. And oftentimes, you say, well, I was not very lucky because in order to cross, I have to go 500 meters that way, cross, and then come back 500 meters again, simply because the next crossing is far in both directions, forward and backward. It happens, right? You cannot have red lights everywhere for pedestrians. This will be very nice for pedestrians, but this will make the traffic flow very, very, very slow because cars will have to be stopping every few, 100 meters, and this is not efficient. So normally, B is the control operator, and then as a, say, the person in charge of controlling the system, you have a lot to say about how to design the B, right? It's the same when you have a building, and then you have to design the emergency exits in case there is some kind of accident or fire or an earthquake or something. You need emergency exits to evacuate this building. Then, as you know, of course, it's relevant where these emergency exits are placed, where the elevators are placed in order to transport people from the basement to the upper floor and vice versa. How many elevators? Where are they collocated? I mean, all this is part of this, say, controller design aspect of control systems. So what does B do? A was a square matrix, n times m, n times n. But the matrix B is not a square, right? So the matrix B is n times m. Why? Because you take a control U, which has components U1 to UM, and the action of these M controls, M could be just one, for instance, just one elevator for the whole building, right? Or just one, say, actuator to regulate the, the flow of air conditioning in the whole building, right? Just one policeman to regulate the traffic in the whole intersection, right? Just one actuator. The action of this actuator has to be distributed into the different components of the system, right? So the impact, the action U has an impact on every component, and this impact is determined by the matrix B, right? So in particular, when U is equal to 1, when M is equal to 1, there is only one U, UT. This UT is multiplied by the different components of the vector B, and this produces the right-hand side of the system. Okay, so this is the paradigmatic control or controllability problem. So the question, just to summarize, is given a finite dimensional system governed by the matrix A, given a control operator B governed by the matrix B of dimensions, n dimensions for the state and m dimensions for the control, given a time window, a time horizon, 0 capital T, given some initial configuration, the position, the situation of the system now, can I guarantee that this, say, state can be driven to the final terminal chosen state through the choice of a suitable control? Okay, this is the problem we have to understand. And how we address this problem? So it's very natural. We use the variation of constants formula. What does the variation of constant formula? It says, well, this is very classical in the theory of ODEs. If you give me this ODE with this initial datum and this applied force, right? We know that the theory of ODE says the solution of that system, which is unique, of course, exists, is smooth and is unique, is given by the solution of the free system. Right? This is just the solution of the system when F is equal to 0 in the absence of any applied force. Taking the initial datum x0 is the solution of the free system, plus the solution of the system taking the control F, in this case BU, in our practical application to control BU, right? Under this integral sign, right? So that, of course, the initial datum here is equal to 0. You take here t equal to 0, the integral goes from 0 to 0, and this goes away. This is the solution of this system, is the solution of the free dynamics plus the particular solution with the right-hand side BU with the initial datum equal to 0. That's it, right? You could check here very easily that if you compute the time derivative here of x prime, right? I will have the time derivative of this. So when I compute the time derivative of exponential at, I get an a, right? On the other hand, when I compute the time derivative here, right? When I compute the time derivative here, I will have the time derivative with respect to the extreme of integration. So I will get the value of the integral at s equal t, and this will give me exponential at of t minus t, which is 0. Exponential a0 is exponential 0 is the identity. So I will simply get here plus b, right, ut, but I will also get a term in which I compute the derivative here within the integrand, and this will kick me another a, right, term, right? And then you see immediately what we wanted, right? Because x prime, right, is equal to a times this term plus a times this term. This is simply ax plus but, right? So this is the verification that out of this variation of constant formula, I do get the solution of the control system, right? The applied force being, in our particular case, but, right? So you see that this is a typical problem in which, yeah, I'm solving the forced, dynamical system, but the applied force F is not arbitrary, in particular because, the range of the forces I can apply, right, is always included in the range of the vector B, right? So out of all possible forces, I can only apply those that are realizable, accessible, doable through the control operator capital B, okay? But the formula for the solution, of course, out of the variation of constant formula applies. Now, what about the initial datum? Well, the initial datum is very simple. If you ask me to compute x of 0, I know this is identity times x0, so it's x0 because exponential of 0 is identity, plus, and this gives me 0. Why? Because I am integrating from 0 to 0, so the initial datum is x0. So this is the solution of the system. We have it here. Okay? And now you see the question you are asking me is, can I drive the system to a given target that I can denote by x1 or xt? Can I make a suitable choice of u so that this is equal to xt? So what is the equation you have to solve? You have simply to solve this equation. You take small t equal capital T, right? So you take here capital T. Whenever you have a small t, you take capital T. And this is the equation you have to solve. That's all. So the controllability of a linear finite-dimensional system is just solving this algebraic system. So in this algebraic system, this term here is completely given. This is the destination to which the free dynamics will arrive. Okay? So if you want to, right, you can also put it here on the right-hand side as part of the target, and you can simply remove it from here. So then, this is, I claim, a linear finite dimensional system. Why? Because this vector here lives in Rn. So there are n equations to be fulfilled, right? And what is the variable I have to my disposal? I have the variable us, right? So I have the possibility, for instance, of taking u, a function which is L2 or L1 with values in Rn. So you see, I have n equations to fulfill the dimension of the system, right? So how many offices there are in this building? Maybe the building is huge. Maybe I have 352 offices. So n is 352. But the number of equations here will be always finite when I am working in this finite dimensional setting, while the controls are depending on time and are therefore living in the Hilbert space of functions that are measurable and square integrable with values in Rn. So you see, there is only one control or m controls. M can be very small, it's finite. But I have the free choice of the control for every time instant. So what is the dimension of that space? We say there are n equations, and I am allowed to choose u as I want in order to fulfill these linear equations, these linear n equations. What is the dimension of the space u that I have at my disposal to do it? Does anyone know what is the dimension of the space L2 depending on time with values in Rn? In Rn? It's infinite. Thank you. Thank you, too. It's infinite. So you say, well, then it should not be that difficult, right? I have a finite number of equations, and I have an infinite amount of, say, components to solve it. So I should be able to do it, right? I should be able to find a vector u out of an infinite dimensional, this infinite dimensional space, just to fulfill, right, n equations, right? Is that possible? Well, you see, it's tricky. So when you start checking examples, you realize immediately that it's not just as simple as counting dimensions. It's not just checking how many equations I have to fulfill and how many controls I do have, right? So this is a very simple example. This is the case where the matrix A is diagonal. You could also make it more general and take here lambda 1 and lambda 2, right? And then you see, in that case, the system is diagonal. It means that in the free dynamics, right, in the dynamics given by A, there is no interaction between one agent and the other. There is no communication between one office and the other, right? Therefore, X1 has its own dynamics and X2 has its proper dynamics, right? The system is diagonal. And then the control, you have just one control, right? And you have chosen the control operator to be 1, 0. So when you write the system, right? When you write the system, what you see is that the control U is having an impact on the component X1, right? But there is no action at all on X2. Of course, because U is acting on X1, you can control the X1 component of the system, but the X2 component of the system, there is nothing you can do. So if you were drawing, right, the dynamics of this system in X1, X2, and you give me some initial datum, according to this analysis, right, if you tell me, okay, my target is going to be this one, I will tell you, well, listen, the only thing I can do is control the X1 component of the system. So maybe I will reach here, or maybe I reach there, right? I can't guarantee that I control the X1 components of the system. So I will get to this vertical line. But I can never guarantee that I will be able to get, to the point you wanted. Why? Because the second component, X2 of the system, is uncontrollable. Why? Simply because U doesn't have any impact on X2. X2 is simply given by exponential t times X0. It does what is the S20, the initial datum, the second component of the initial datum. It does what it does, and is completely independent of the value of U. So this gives you a system in which the number of components is 2, the number of controls is 1, so there is not a big gap in terms of the dimensions of state and control, just a gap of 1. But the system is not controllable. Okay? So then, well, maybe the conclusion then should be that I have to use as many controls as the dimension of the system. If this was the conclusion, the theory will be very deceiving, right? Because it's not really realistic. Maybe you can do it when there are only 2 components of the system, but when you are talking to a very large population, the population of a big town, 10 million people, I mean, n is equal 10 million, you cannot expect to have 1 control per person, right? Okay, so now let's look to a different case. Let's look to the harmonic oscillator. This is a second order in time equation. As you know, this is the linearized equation for a pendulum, right? The linearized equation for a pendulum, which is now being controlled by a force. You will say, well, in principle, we could say this doesn't fit into the context of the A-B systems I am considering, because this is second order in time. Well, yes, it's true, but we know that every second order in time ordinary differential equation can be written as a system of first order in time equations, right? So for this, the only thing you need to do is to say, okay, I introduce the scalar auxiliary variable y, which is the velocity, and then I can write the system as y double prime equal minus x plus u, right? So then in the new state, right, so there will be a new vector, which is now composed by x and x prime. I know that in this new vector, then the system looks like the A-B system first order, in which now the matrix A is anti-adjoint, right? So I have 0 identity minus identity 0. Why? Because the first derivative of x is y, which is the second component. So there is a 1 here. And then the first derivative of the second component, sorry, here it should be just 1 prime, right? 1 prime, which is the second derivative of x. The derivative of y prime is equal to minus x, so it means there is a minus 1 here. And the control operator, the control u, is acting only on the second component. There is no control on the first component, so the control is simply 0, 1, right? So u is multiplied by b, so that u times b gives me 0 in the first component and u on the second component. So you see that again, we are in a configuration in which n is equal to 2 and m is equal to 1. But my claim is that in this case, the controllability of the system is guaranteed. So actually, there is a more general remark, is that regardless of how high the order of the differential equation is, whenever you are considering ordinary differential equations which are scalar, regardless how big the order n is, just one control suffices to control the system. What is the reason for this? Well, the reason is that precisely you are in a very lucky situation where maybe the dimension of the system n is equal to 2 in this case, but I could take here a differential equation of order 298, then n will be 298, n will still be 1, just the control on the right-hand side, and I can guarantee the controllability of the system. Why is that? Well, because you see, if you are here, for instance, in the, undo the drawing in R2, what is our requirement? Our requirement is that you give me a point in R2, the initial datum, you give me a final point, an arrival point there. So the only thing I am asking you is whether you can find the U so that the solution of this harmonic oscillator problem will match, you know, this initial datum to this final datum. But of course, also, you know, looking also to the derivatives, right? Because, you know, when you impose the initial datum and the final datum on the position, I'm not only interested on the position, but also interested on the velocity. Fine. But after all, it's about linking 2 points in R2. So how do I choose controls U that are linking these points? Well, there are many ways. There are as many ways of doing it as paths there are, you know, linking, you know, the initial datum and the target. I could do it in a straight line, in which case x will be a linear function so that the second derivative is equal to 0. Then the control U will be precisely x. I could do it oscillating, maybe to avoid some obstacles, or because just I have plenty of time, and then I want to spend my time walking around and visiting the landscape. So I do it in an oscillating manner. So in that case, of course, there is some acceleration. X double prime is non-zero, so the control is more complicated. So you see, this is a trivial situation in which you can build a trajectory. So the controllability of the system is obvious. You can build a trajectory and just do it. And out of that, you can read off the control as being the output of differential operator on the trajectory. So this is a very nice example to see that the controllability is not a matter of dimensions. In the previous counter example, n was 2, m was 1, and you could not control the system. Now, n is 2, m is 1, and you can indeed control the system. So what's going on? Actually, in this example, we see this is a very natural source of examples where the dimension can be arbitrary, and just with one control, you control the system. What's going on? Okay, so you will find sometimes terminology that is introduced in order to address these kind of problems. This is not absolutely necessary, but I just mention it to you in case you see it written. So for instance, people will tell you about the set of reachable states. What is the set of reachable states? Well, so you see basically what we are doing, right? We are in Rn. In this drawing, n equals 3, but n is arbitrary. You are always working in the Euclidean space that you can draw just by placing, the origin arbitrarily at that point. And then we are given some initial datum, right? x0. And what are we doing then? So what we are doing is just, building trajectories. So you give me a u, and this will give me a trajectory. You give me another u, and this will give me another trajectory. You give me another u, and this will give me another trajectory, another u, and this will give me another trajectory, another u, this gives me another trajectory, another u, this gives me another trajectory. So, of course, when you are choosing the different controls, right, at time capital T, you will be visiting different final destinations. And the problem of controllability is precisely, right, to be able to show that the set of all points you are able to visit, right, is simply Rn, right, as indicated here. Okay. Of course, in practical applications, there you will have often controls, right? Often in practical applications, you have constraints. So the constraints are, for instance, well, the norm of the control I can afford is limited by some m, right? And the time is given. Normally we work on a finite time horizon. There is a deadline for submitting the articles to that conference. So I have, 1 month or one month to submit my proposal to the funding agency. So there is a deadline, there is a time horizon, right? Then there is, in your team, you are 3 people, but you are not 40 people, you are 3 people. And then 3 people have to share the job of preparing the proposal, right? So there is a constraint also on the amount of work you can deliver, right? And this is the M. Then in those cases, of course, the reachable space, the reachable set, it will be a set, will be also limited in size, right? So, but then, it is still interesting to understand whether you have the controllability without constraints, because whenever, the system is fully controllable, right? It means that in the absence of control, the constraint, you will get everywhere, right? In the presence of constraints, of course, your ambition has to be limited in size, but you still know that you can drive the system in any direction, right? So the controllability property, even though a posteriori, you often need to deal with it in the context of constrained problems, doing it first in the unconstrained case is very interesting. Because when the system is controllable in the unconstrained case, meaning that you can get anywhere in the space without constraints, in the presence of constraints, it simply means that your arrival set will be a disk, will be a sphere, will be limited, right? But, it will always contain all the possible directions of the system. Okay, so now the question is, how do I see all this, right? So we said the characterization of the solutions is given by this variation of constant formula. And all the controllability problem is about solving these equations. There is plenty of room to do it because I have just n components and many controls, infinite, dimensional space of controls. Yet we have seen that despite of this dimensionality, apparently dimensionality easiness of the problem, in some cases it works, in some other it doesn't work. How do I really see in this kind of formulation whether the system is controllable or not? Okay, so in order to do this, it's very interesting to introduce the adjoint system, right? So there are many ways of introducing the adjoint system. You have seen it often through Lagrange multipliers. You have seen it through integration by parts in the theory of distributional theory for partial differential equations. You have seen it maybe in the Pontryagin maximum principle, if you ever did that, and so on. But this is always a central concept in control, right? So what is the adjoint system? So let me first tell you what is the algebraic definition of the adjoint system, right? So the adjoint matrix, you all know what it is, right? So given a matrix A, you can always define the matrix, the adjoint matrix A star, right? So that the adjoint matrix A of A star of a matrix A is just changing, interchanging columns and rows. And from a purely algebraic perspective, what you are doing is that in the scalar product AX times Y, you are able to isolate the variable X, putting the action on A of A into Y through the adjoint A star. That's all. This is a pure definition of the algebraic adjoint. On the other hand, right? On the adjoint, you reverse the sense of time as well. Plus into minus. On the other hand, on the adjoint, because you have reversed the sense of time, right? You don't take the initial condition at t equals 0, but you rather take the condition for the Cauchy problem at time t equal to capital T, right? Of course, in the context of ordinary differential equations, this doesn't really matter, right? So I can apply the classical theory of, ODEs, and then I know that this system will have a unique solution, and then the solution can be written. Maybe you can help me on this. It will be what? It will be the exponential of A star, I think, t minus t multiplied by phi t, right? Is this correct? Let's check. If I take phi at t equal capital T, I evaluate this exponential at small t equal capital T, this goes away, I get the identity, and I get phi t. So, the initial datum at t equal capital T, the Cauchy value at t equal capital T, phi t is taken. On the other hand, when I compute the time derivative of phi, I have to take the time derivative of this exponential. There is a minus coming out. There is an A star coming out, and I get indeed minus A star phi. So that's fine. So you see, in the finite dimensional context, this is not a problem. Of course, when you are in the context of semigroups, you know that you have to be careful because there are semigroups generated by anti-adjoint operators like the wave equation or the Schrodinger equations that are time reversible. So the sense of time doesn't really matter. But when you are dealing with dissipative semigroups, like for instance, generated by a self-adjoint operator like the heat equation, the sense of time is extremely important because the heat equation is well posed in the forward sense of time, but is ill posed, even extremely ill posed, in the backward sense of time. Okay? So, but in the finite dimensional context, you can always define the exponential of a matrix or the exponential of minus that matrix. This is always well defined. Okay? And then, you see, I claim the following. So, assume that my goal in the control problem was, to drive the system to zero, right? The system being linear, right? In fact, you don't need to consider all possible targets. You can just consider all possible initial datum and wonder whether you can drive the system to zero. Assume my goal was simply driving the system to zero. Zero as a representation of a very simplified final state I could, try to achieve. Then my claim is that if my goal on the control system is to drive the system to zero, I can rid of this goal through the following, say, duality identity, right? So this looks, in the beginning, this looks strange, right? Because, so here you see I have controls with, I could maybe emphasize values in Rm, and I say the control U is successful on driving the initial datum x0 to the zero equilibrium. Zero is an equilibrium, right? Because A0 is equal to zero. Therefore, in the absence of control, zero is always a steady state solution of the system. So the control U is successful on driving, right, the system, the control system to zero, if and only if this equation is fulfilled for every phi solution of the adjoint system. Okay, but you see, when I say that I do it for every phi solution of this adjoint system, right, is the same as saying that I do it for every phi t, the Cauchy value of that system, taking into account that phi t is in Rn. But the system being linear, what is the dimension of a space of initial data is just n. Phi t is in Rn, right? And therefore, checking that this is true for every phi t in Rn is equivalent to checking that this is true, right, for every vector Ej, for G j from 1 to n, E1 En being the canonical basis of Rn. You see that again in here, although it looks that this variational identity, you know, is constrained by many phi's, actually in this identity there are just n equations. So this is just a way of writing the same controllability condition as for the original system, writing it in this duality manner using the adjoint as test function, the same you do in the theory of distributions. How do you do that proof? Why, you know, the controllability property of the original system, right, which is, right, written here, why this controllability property when the target is simply 0, in the simplified case where the target is 0, why this controllability property is equivalent to this dual version? Well, the proof is very simple, right? So you say, okay, what I do is I just take the equation satisfied by x and then I multiply scalarly by phi, right? So I take the equation satisfied by x and I multiply scalarly by phi. So here the bracket, right? These brackets is a scalar product in Rn, right? So that I take the n components of x prime and I multiply by phi. X prime being ax plus bu, I get ax scalar phi plus bu scalar phi. This is the first identity, it's just trivial. This is, of course, true for every time from 0 to capital T, because the ODE x prime equal ax plus bu is fulfilled pointwise with respect to T. Now, I go to the equation satisfied by phi prime, phi, which is minus phi prime equal a star phi, and I multiply scalarly by x, right? Okay, so here the scalar product is symmetric, so I put it on the left, on the right, doesn't really matter. I have this identity again for all t between 0 and capital T. Now I take this identity and I subtract this quantity to this one, and then I realize I have x prime times phi plus x times phi prime. This is the time derivative of x phi. This is the time derivative of x phi, right? Because I am subtracting this and this, I will subtract this and that. But you see, a star is the adjoint of a, therefore ax phi is the same as a star phi x. So this goes away, and the only thing I get is b phi. So you see that thanks to this duality game between a and a star, and the equation fulfilled by the state x and the adjoint state equation fulfilled by the adjoint phi, the equation reads simply like this. So what this equation is governing is telling you is that actually, right, when you look to the action of phi on the original system, you can track, right, the projection of x phi just by computing, right, the action of the control bu on phi. Fine. So this is a very nice identity. Now I integrate this identity. I say, okay, I have it. I integrate it from 0 to capital T because this is just my time horizon, right? So all in this problem is done to work in the time horizon I am given, 0 capital T. So I integrate with respect to T. What do I get? I get the scalar product of x phi at time capital T. At time capital T, xt, I don't know. This is precisely the object I'm trying to control, but in principle, given a u, you know, the x will get where it gets. I don't know exactly where the x will get. I know that the value of phi, of course, at time capital T is phi t, because this is something I can choose. It's actually the Cauchy value of, you know, of the adjoint state at time capital T. So I have the scalar product of x phi at time capital T minus the scalar product of s phi at t equals 0. And at t equals 0, I have x0, the initial datum for x. And then, of course, I cannot guarantee what phi 0 is, because phi is the solution of the adjoint system departing from phi t at time capital T that I have to solve, right? And this, when I integrate with respect to time, is going to be the integral from 0 to t of bu phi, that if you want to, I can also write that way, the integral of 0 to t of u b star phi. But now, what I say is that the if and only if condition, so that you guarantee that the control u is successful on driving the system to equilibrium, to xt equal to 0, is that this is 0 for all phi t, and therefore everything is condensed into that identity, the identity I wrote. And this is a different way of writing it, just putting them together on the same side of the equation. So you see that this is fully equivalent to the controllability property. Now, when you look to this, you say, well, this is the unknown u, right? This is a bilinear form. X0 is given. This is a linear form. This really reminds me a lot of the Lax-Milgram lemma, right? So you remember the Lax-Milgram lemma, right? So Lax-Milgram says, okay, I take a bilinear form on a Hilbert space. Just to make it simpler, I assume that A is symmetric, although there is a generalization of Lax-Milgram for non-symmetric bilinear forms. I assume it is coercive. I assume it is continuous. And then the Lax-Milgram lemma says that, you know, for every element f on the dual H prime, right, there is a unique solution u belonging to H, so that AUV is equal to FV for every V in the space H. This is what the Lax-Milgram lemma says. And it says something more. It says, you know, Lax-Milgram tells you also, listen, not only there is a unique solution for this variational problem, but actually you can find it out of the calculus of variation. In order to do it, you just need to minimize this quadratic function. If you minimize this quadratic function on the space H, then you have the minimum of the functional J, but you also have the solution of this variational problem, right? And in order to minimize this functional, then you simply apply the direct method of the calculus of variation. You see it presented in the introductory books of functional analysis to PDEs, like the book of Brezis or the book by Evans. I can give you the references if you like. And this is very, elementary. You say, well, the only thing I have to do is to, define the infimum of the functional J, build a minimizing sequence, show that the minimizing sequence is bounded because of the coercivity of the form and the functional. Then the minimizing sequence is bounded. I am in a Hilbert space. I have a weakly convergence subsequence. I take the limit, and this limit is the minimum. Why? Because the functional being convex and continuous is weakly, lower semi-continuous, and that's it. I have the minimum. Good. So then when you think on all these, you say, well, but then my goal was to solve this equation, sorry. my goal was to solve this equation. And when I look to this, I see some clear analogy with last milligram. Actually, my claim is that if I want to solve that equation, it is sufficient for me to minimize this functional. So this is where you start seeing how out of a control problem that is formulated in the space of the state X and the control U, the problem becomes, by duality. The problem is shifted, is translated into the adjoint world, in which now there is no control anymore, and it's just about minimizing this functional on the space of solutions of the adjoint system. Okay, let's go further. So my claim is the following. I claim, by analogy with last milligram, that if I am able to minimize this functional, I have the control I need, right? So I will give you the proof now. But before I get into the proof, so let me explain it how it really works. I say, okay, you want to control x0. You want to control x0 to 0 for the system given by A and B. Then the algorithm you have to implement is you take this functional. What is this functional doing? Well, it's just, you take the adjoint system. So for every phi t, you compute the solution phi of this adjoint system, right? Out of phi, you have phi 0. You do the scalar product of the initial datum x0 to be controlled with phi 0. On the other hand, out of the adjoint system, you have the vector phi, is the solution phi, depending on time, which has n components as the state x. You apply the matrix B star. So recall that B is a matrix n times m. So B star is a matrix m times n. So you are taking the n components of phi, you are multiplying it by the matrix B star. So this gives you, right, an m-dimensional vector. You see in particular that when m is equal to 1, when there is just one control, this bi star phi is just a linear combination of all the components of phi, right? So this is like if you have a vector which has a very large dimension, phi 1, phi 2, phi 3, phi n, but out of this column vector, you just see a linear combination of all the components. You don't see each component, you just see a linear combination of all of them, right? Okay. Then you cook this quadratic term here, right? You cook this quadratic term. And this is the functional I claim I have to minimize, right? And the claim is, if the minimum of this functional is achieved, you have the controllability. And the control is simply bi star phi hat. Hat here is nothing to do with the Fourier transform. This is just a notation for the minimizer. So you see, this proof is very nice for several reasons. First, I will completely get rid of the original problem in which I have to deal with the variation of constant formula, build a control U in order to control the X. I forget about all this. I just work in the space of the adjoints, and my only concern is whether I can or not minimize this function. This is the first thing. But the second thing is that this will become also algorithmic. Because if building the control is just saying that U is equal to B star phi hat, and phi hat is just, is just the solution of this adjoint system with a very distinguished initial datum phi, which is given by the minimizer of that functional. Once I have the minimizer, I just solve this ODE, something that I can do numerically if the system is complicated, as it will always be in practical applications, or most often. I will use some numerical integrator, and that's it. So I not only have a proof, but I also will have a constructive algorithm, right? Okay, so now why the minimizer of this in this form? is the control I like? Well, it's very simple. You say, assume I have a control, a minimizer. If I have a minimizer, I know that the Gateau derivative, this will be a critical point of the functional J. So I will have that the Gateau derivative of this functional is equal to 0. Okay, good. How do I do that? Well, I take the functional J and I just compute the Gateau derivative. How do I do it? Assuming phi hat t is the minimizer, I do a small increment with respect to a small h in any of the possible directions phi t in the space. I compute the Gateau derivative, and as it is typical, right, in the quadratic problem become linear, and the linear functional stays. So this is immediately the derivative equals 0 I get out of the criticality of the minimizer phi t hat. And now you say, okay, how do I compare this? How do I compare this with the equation I had for characterizing the control? Well, I realized that this was exactly what I needed for the control ut. So, you know, the proof of the fact that if this functional has a minimizer, this minimizer gives me the control is just writing the Gateau derivative is equal to 0. And now you say, okay, what do I need in such a context? You see, this problem looks very complicated because it goes through the, you know, the adjoint equation for phi. But after all, right, this functional J is a functional that is, you know, defined in our Rn is defined in Rn with values in R, right? Why? Because the functional is actually defined on the space of initial values I can give to the adjoint state at the time capital T. So this is just a quadratic functional on a Hilbert space. In this case, the Hilbert space is just Rn, the Euclidean space, and I just need to minimize it. What do I need to minimize this functional? Well, I apply the direct method of the calculus of variations, and the only thing I need is just to check the continuity, because this is clearly, sorry, the coercivity, because this is clearly convex. This is clearly continuous, so my only concern is whether this functional is coercive, right? And what does coercivity mean? Coercivity means that the limit as the norm of the argument goes to infinity of j phi t goes to infinity as well, right? So I'm really dealing with a paraboloid that is going up to infinity at infinity. This is what I need in order to minimize a quadratic function. Of course, if the functional was not you know, really a paraboloid, a coercive paraboloid, there will be directions in which the paraboloid is oriented negatively. And therefore, if you will ask me to the minimizer, I will tell you there is no such a minimizer. The minimizer is at infinity, and the minimum value of the functional j is never achieved. It is an infimum, and the infimum is minus infinity. So the only chance in which this quadratic functional can have a minimum is just by coercivity, right? And this is in agreement with precisely the fundamental observations of the direct method of the calculus of variation. What does coercivity mean? Coercivity simply means that the quadratic term has to dominate the linear term. That's all. And this, of course, because we are in the context of, right, a linear finite dimensional system, right? It is the same, saying that the quadratic form is able to dominate the norm of the initial datum at t equals 0 or at t equal capital T. Why? Because as we have observed, right, we have said that, you know, phi t was, help me please, I think it was exponential a star t minus t phi t. Therefore, phi 0 is simply exponential A star T phi T. And then out of this formula, you can always claim that the norm of phi 0 is less than the norm of the matrix exponential A star T phi T. But you can also invert this formula, say that phi T is exponential minus A star T phi 0, and therefore you also have the dual inequality phi T less than the norm of the, reverse matrix times the norm of phi 0. Of course, when you write down the inequality on the observation of phi 0 or on the observation of phi T, you don't get the same constant small z or large c, because the constant will change because you have to multiply by one factor or the other, right? So here actually should be the norm of the operator times phi t, right? So these two constants are not the same. But the fact that the coercivity is fulfilled can be written in these two norms, because these two norms for a differential equation in Rn are completely equivalent. Okay. And this is what in the context of control is often called as observation or observability inequality. And this is actually in agreement with the key definition that Norbert Given gave, you remember, for the topic of cybernetics. He said, is the science of communication and control in animals and machines. So he said communication and control. He didn't say communication or control. He said communication and control. So you see it here reflected. You are able to control the system in the space of states X if you have a good communication device on the space of the adjoints phi. Why I'm talking about communication or observation? Well, because you see, we are in the finite-dimensional space. So all this is just, a kind of, a strange seminor, right, that I could denote by some, say, asterisk in the space Rn. It is true that it's a kind of a strange seminor, right? Because the seminor says, take phi t, and rather than computing like in the Euclidean space or, typical norms, I'll just take some weighted square sum of the components and so on. So here we cook the norm in a very complicated manner. We say, I take phi t, I solve the adjoint system. Out of the adjoint system, I multiply by b star, right? And then I take the square, and then I integrate with respect to time. So this is quite complicated, but after all, it's just a quadratic form in Rn. And what I'm saying is that we know that in Rn, all norms are equivalent. All norms are equivalent, and because of that, right, the only thing I need to show that there is a constant that will be able to dominate the norm of phi t out of this observed quantity is just the fact that this is a norm. And the fact that this is a norm is just reduced to the fact that does the fact that b star phi is equal to 0 for all t imply that phi is equal to 0 everywhere? And this is why I say observation. Why? Think on the specific example I gave you where m is equal to 1, just one control. So what I'm seeing here is just a combination of all the components of phi 1, phi n. I'm just seeing one combination out of all of them. So, I'm watching a very complex scene, right? So, I have a very tiny window through which I can observe. There is many people in that room, and I just need to observe whether I will be able to, I have to determine whether my observation will be sufficient to recover full information of the state. This is actually very much related to traditional problems like inverse problem or identification problems, right? This is what happens often in, complex systems. So you are a material scientist, and someone, you are working in a laboratory of material scientists, which is expert on, identifying the components of a material, right? This is like on your iPhone, right? There are very nice tools which allow you to, given a picture, right? You can just take, a few pixels, and then you can ask to your telephone software, can you please analyze what are the different, say, colors that are mixed in this pixel? And then, the software will tell you, okay, I have 10% of blue, 15% of yellow, and 13% of green. Will give you the decomposition. So you are a material scientist, I bring you a material, and I ask you, could you please tell me what this material is? Well, what you will do is you will do a number of experiments, and out of a number of experiments, you will try to determine what the material is. So here, this is what we are doing here. We have a sensor. We are trying to identify the system, the state of the system. We have a sensor, right? So B star is just a sensor. How many sensors do I have? Well, I have M sensors. It's the output of this measurement. And out of this measurement done during the time interval 0t, I need to be able to determine fully the state, right? So then you see that because of all this duality between state, control, and observation, the problem of controllability is reduced to a problem of observability that you can also, right, in the context of analytic functions and partial differential equations, this is called a unique continuation property. Why unique continuation property? Because, of course, if you give me the measurement B star phi equal to 0, guessing that phi is equal to 0 is a very natural continuation of this information. It's a very natural extension. The question is whether this is the unique one, right? And as you know, for instance, if I ask you, right, is it true that a function that is 0 to the left will always be 0 to the right? Or are there functions that being 0 to one side, then they can take off smoothly in a non-trivial manner? Do these functions exist or not? And the answer is, well, it depends on the class, right? So if you are talking about analytic functions, the question is no. The answer is no. You ask me, are there analytic functions taking value 0 to the left and then taking off to the right? The answer is no. So if someone sells you an airplane ticket, very cheap, right, to go from Beijing to Shanghai, they tell you, oh, very cheap ticket, and the flight is very smooth, it's analytic. You say, no, I don't buy the ticket because I know that with an analytic flight, I will never be able to take off. Because if the trajectory is flat, it will continue being flat. This takeoff is impossible in the class of analytic functions. Why? Because analytic functions at this point of takeoff, you can do a power series expansion. Therefore, the solution is, the function is given on a neighborhood of this point as a power series. And the power series coefficients are just the derivatives of the function. But the derivatives of this function will all be 0, right? Because the function is 0 to the left, and therefore all the derivatives will be equal to 0. So the function will be always 0. But in say infinity, it is possible, right? Could you please tell me, and we stop now for a break with the answer to this question, could you please tell me which is a say infinity function that looks that way, which breaks down the principle of unique continuation? Maybe you can write simply on the chat. Do you know any function that is 0 to the left that takes off non-trivially and which is, say, infinity smooth? Of course, the function cannot be analytic, right? Because as we said, if the function was analytic, it will be 0, will be unique continuation. Do you know any such as say infinity function? This is a classical example, right? Where when you try to make the difference between the class of say infinity functions and analytic functions, this is precisely the kind of functions you look at. Those that are breaking the rule of unique continuation. Because then they cannot be represented by power series. Yeah. So the example is just exponential of -1 over x squared. So this is an elementary exercise you can do. Draw this function. You see that this function is precisely taking this shape. You can check that this say infinity is smooth, but of course, by construction, it doesn't fulfill the property of unique continuation. Okay, so then we have reduced the problem to this unique continuation question. And then in this way, we have materialized this, say, duality perspective of control theory, that Norbert Wiener formulated cybernetics about control and communication. So you see that out of the unique continuation for the, say, adjoint system, simply because of the fact that B star phi during 0 and t, simply because B star phi during 0 capital T implies that phi is equal to 0, we have the unique continuation. This guarantees the observability inequality. This guarantees that the functional J has a minimum, and this guarantees the controllability. Okay? So, and as I said before, this is not only an analytic way of analyzing the controllability property, but it gives you a constructive way of, say, building the actual control. And this is precisely what you want when you are also in a context of, say, data science or machine learning. It's not about, is there a neural network that does that and that? No, okay, of course you are interested on that. But you are even more interested on being actually capable of building the neural network that is achieving the goal you have, right? So in practical applications, this kind of characterization is not only useful because it gives you a nice analytical manner of handling the problem, but also because it leads to a constructive computational method. And now that we have done all this, now it's very easy to understand why the Kalman rank condition is sharp. You remember I told you the other day, I said, eventually, whether a system is controllable or not, it becomes this purely algebraic condition, or whether the rank of B, AB, A squared B up to AN minus 1B is equal to N, right? And as we said the other day, because this condition is purely algebraic and the time horizon capital T is not involved on it, right? The controllability property holds in some time horizon if it holds in all time horizon, right? So as soon as you have this rank condition, the system is controllable for all capital T. And if the condition is not fulfilled, the system is never controllable, right? Let me give you the proof, right? Suppose first that the rank is N, right? There are two implications. So I suppose that the rank is N, and I would like to show that the system is controllable. But actually, we have shown that the controllability of the system is equivalent to unique continuation. So let us then, under this condition of full rank, let me assume that there is a phi so that B star phi is equal to 0. how does phi look? Well, phi is a solution of the adjoint ODE, so it takes this form. Therefore, it means that B star A star T minus T phi T is equal to 0 for all T. Let me compute the value of this, say, B star projected trajectory at T equal capital T and all the consecutive derivatives. You see that whenever you take a derivative of, with respect to a small t, out of the exponential, you get a power of A star. So you see that because B star phi is equal to 0, right, then all the derivatives at T equal capital T are equal to 0. And therefore, B star A star to the power K phi T is equal to 0 for all K. Actually, these and these are completely equivalent because phi being a solution of the adjoint ODE is represented by this exponential form, and therefore is an analytic function. So, but in particular, this is true for all K. Now, this being true for all K, it means that phi T is in the kernel of this infinite matrix, right? In particular, it is in the kernel of this finite projection of this matrix. But, the kernel of this matrix is equal to 0 if and only if the rank of the adjoint is equal to n. So because the rank of the Kalman matrix is full, the kernel is 0, and then the only phi T fulfilling all these null conditions, which is equivalent to B star phi is equal to 0, is phi equal to 0. That's the first proof. Now, let us do the second proof. Let us now show that the rank being full is not only a sufficient condition, but is also a necessary condition. So let me assume that the rank is less than n, right? So let me take a pathological situation in which I am trying to control a system, but when I check the Kalman rank condition, I say, oh, I don't get n, I don't get full rank, I get less. So maybe n minus 1, n minus 2, n minus 3, and so on. If the rank is less, right, then the kernel is non-void. The kernel of the adjoint is non-void. So there is an element phi T, which is, in the kernel of all these matrices, right? In principle, right, out of here, you only get it for K from 0 up to n minus 1. But the claim is that if phi T is in the kernel of these operators, B star A star K, for K from 0 to n minus 1, then it's also true, it's also in the kernel for all other powers of K. Why is that? It's because Cayley-Hamilton indicates that, every matrix is a 0 of its characteristic polynomial. You can apply Cayley-Hamilton also to A star. That will also be a 0 of this characteristic polynomial. And this means that once you know that phi T is in the kernel of these operators for K from 0 to n minus 1, then for all the consecutive powers, it will also be on the kernel. And therefore, phi T will be in the full kernel, right, of the exponential function generating, the adjoint ODE. In other words, B star phi T will always be equal to 0. Why? Because B star exponential A star can be expanded in power series out of all the possible powers in here, right? So let me here remind you, and this is where, in the finite dimensional setting, things are much simpler, is that, given a matrix or in general, a bounded operator on a Hilbert or Banach space, you can define the exponential of that operator, right, by just writing the sum for K greater than 0 of AK divided by K factorial, right? Okay, very good. So the same, you can do it here, right? And then you can say that exponential of A star t minus s is the sum for k greater than 0 of t minus t to the power k, A star to the power k divided by k factorial. And if you multiply everything by b star, right? You have here everything multiplied by b star, then you see that, you know, being phi t in the kernel of these operators, it means that phi t is also in the kernel of this projected semigroup. Okay, so you see that by contradiction, as soon as the rank is less than n, there is a non-trivial phi t, which is in the kernel of these operators. Therefore, you know, this projection of the corresponding trajectory is equal to 0. You have lost the observability. And because you have lost the observability, then you see that when you look to how this quantity evolves, remember that, recall that, you know, the derivative of xt was equal to, you know, the integral of the control times the trajectory, right? What you see that this is completely invariant. So you see that this projection of the solution xt can never be controlled. So what the proof says is that as soon as the rank is less than n, by duality, there is a solution of the adjoint system which is invisible through B star, through the adjoint observation operator B star. And then this invisible non-trivial trajectory of the adjoint is a projection of the state you cannot control. And this is precisely what I said in the first day, is like when you are looking to, you know, the car, right? You know, on the space. The car, we can drive the car is controllable in R2, but the car is not controllable in R3. You don't have the vertical propulsion, right? Okay, very good. So now we have understood what are the main ingredients. We have the definition of controllable system. I mean, we have the definition of control system. We have the characterization of controllability out of Kalman. We have the dual equivalent through observability. Everything is purely algebraic. But what is really important is that you can see controllability out of observability in the sense that this is reduced to a unique continuation property, and that this unique continuation property not only allows you to characterize controllability, but allows you to build a functional that, you know, through minimization gives you the control, right? Okay, so now you can show some very interesting properties, like, you know, in particular, I can always claim that the set of controllable pairs is open, for instance. What does it mean that the set of controllable pairs is open? What do you understand by this sentence? Is the meaning of that clear to you? What does it mean that it's open? Well, the fact that the system, that the property of, in general, a property is said to be open, right? I say that my claim is that if the system AB is controllable, I can say it that way, right? I don't need to write the full x prime equal ax please plus bu in the time horizon 0t. I can simply say the system is controllable because, you know, the controllability property is just independent of the time window. It's just the algebraic Kalman rank condition. I say that if the system is controllable and I take now a different system, A tilde, B tilde, so that the distance between A tilde and A and B tilde and B is small, then I also claim that A tilde, B tilde is going to be controllable. Why is that? Do you have any hint of why, if A, B is controllable, small perturbations of the control system will lead to a controllable system as well? Why is that? This is what it means being open. It means that small perturbations preserve the property. Why is that true? Rank is continuous. That's a very good point, Matt. Thank you. Indeed, you know, AB controllable means that the rank is equal to n. And the rank depends continuously on the coefficients of the matrices. So small perturbations on the coefficients doesn't really matter whether I change the A or the B or both. If I just do it a little bit, the rank is continuous. Right? Okay, very good. On the other hand, the rank is discrete, right? Therefore, it will not jump, you know, from n to n minus 1, right, in just a small neighborhood. Very good. On the other hand, I claim that the set of controllable systems is dense. For instance, in particular, I claim the following, right? I say that given A, you give me a matrix A, right? The set of B's for which AB is controllable is dense. Right? Why is that? So what does it mean to be dense? It means that, you know, if I am unlucky and I find a B so that when I check the Kalman rank condition, the system is not controllable, okay, it's not so bad, because I can always say, well, maybe for this B, the system is not controllable, right? The same you could do, oh, you know, I take a neural network, I wanted to classify data, oh, and this neural network doesn't do it. But if you have this density property, this is not so bad, because you know that a small variation of the system you have generated will have the property you like. This is why we are interested on such a concept, right? We say, okay, I take a B, I control the system, oh, I see that some components are not being well controlled. Okay, I change the B a little bit, and then I can restore, I can, you know, guarantee that the controllability property is fully satisfied. Why is that? Well, because you see, the rank being less than n can be written as, you know, the determinants of the submatrices being equal to 0. And the determinant equal to 0 is a polynomial being equal to 0. It's a polynomial on the coefficients of the matrices A and B. But you know that a polynomial is equal to 0 on very few points, right? So in particular, when you are considering a polynomial on the real line, right? So the number of zeros is finite. When you are considering the polynomial, you know, in the Euclidean space, right? The zeros of polynomials, right, are, you know, constituted by the intersections of the union of manifolds, but all these manifolds, of course, are of zero measure, right? A polynomial is an analytic function. Then it cannot vanish, right, on a set, on an open dense set. So being 0 is something that is exceptional for polynomials, right? And therefore, for the rank condition, the same is true. Okay, good. So you see that, of course, this is not very, you know, in practice, this is very interesting because it tells you that generically systems are controllable. This is not so useful, right? Because I could say the same for numbers, right? We could say for real numbers, we could say, oh, being rational is a dense property. Yes, being rational is dense, being irrational is dense. Yet there are many more irrational points than rational points, right? So the density is very interesting from a, say, conceptual point of view, but in practical applications, right, is not so easy to manipulate. On the other hand, also, I mean, if you give me a number, right, so, I mean, you cannot give me a number, right? So in practice, if you are, you know, putting it in the computer, you will chop off a number of decimals, so you will never be able, whether you are talking about pi, you know, which is irrational, or a rational approximation of pi. So you cannot really rely, right, on the fact that the system will become, you know, controllable, right, just because you have changed the, you know, the 25th decimal on the expression of the equation. So you need something more robust, right? Yet, it's very good to know from an analytical perspective that, you know, the control property is something that generically occurs. You can always succeed by choosing properly small variations of the system, or in particular of the control actuator, right? And it's open in the sense that whenever a system is controllable, the neighboring systems are also controllable. This is, you know, being open, right? Control property being open is related to the important concept in, you know, systems control of robustness, right? So I say that a control system is robust, right, when the control properties of this system are preserved, right, also for small variations of the system, right? So, you know, the air conditioning system of our offices will not be robust if it works only, you know, today, but it doesn't work tomorrow, right? Or it works only today because the temperature is not so high, but as soon as the, you know, the temperature increases, then it doesn't work anymore, right? So a control system, in order to be really usable, to be efficient, to be reliable, we need it to be robust. If it is not robust, it means that the performance of the system will break down as soon as, you know, as soon as the conditions change a little bit, and this is not something we are interested in, right? So when you are, for instance, driving your motorcycle or your car, I mean, you need to rely on your motorcycle or your car every day, right? Because you need to go to, you know, to university every day at 8 a.m. So you need it to be functioning every morning. If it will work only some days, then you have to change the car or the motorcycle, or you have to, you know, bring it to the garage, right, for a reparation, because you need a robust transportation means, right? You cannot rely on, you know, on the subway network in your town if some days the metros are very fast, but some other times they are very slow. You need it to be, you know, you need to anticipate the performance, right? So to be able to say, okay, to be in class at 8, I have to leave home at 7:13, right? And then you can do that every day again and again. Okay, so these are very important properties. The robustness of the control system, something which is less relevant, still intellectually interesting, is the fact that control systems are dense, keeping into account that density is not always as good as we think, because, as I said, rationals are dense on the real line, yet being a rational number is a very exceptional property that only a set of real numbers of zero measure fulfill, right? The next condition is also the next property is also very interesting, is that I have done the computation when, you know, the target is 0. You can do as an exercise the computation, so this is a good exercise for you to do. When the target is x1, And then, of course, the size of the control you will use, right, which will be, again, B star applied to some adjoint phi computed minimizing a suitable functional, right? The control you use will always be proportional to this distance here. What is this distance measuring? What is exponential AT x0 minus the target that, we have also denoted sometimes like xt? What is this distance representing here? Why this distance is the only one entering in the size of the control you need, right? Of course, I could say more brutally, I could say that the control I need is bounded by some big number times the initial datum plus the final target. But this is much more precise. Yeah? The control I need is just depending on this gap. Why is that? What is this gap measuring? What is this gap measuring? Right, if u is equal to 0, the distance, right? So in other words, thank you, Ma. So what this gap is, you see, this is the free solution. This is what we have written before. Exponential ATX0 is just the free solution of a control system in the absence of control, u equals 0. So you see, if you tell me that the free solution, if you were very lucky and this difference was equal to 0, it will mean there is nothing to be done. You just take u equal to 0, you solve the system without control. This system is going from x0 into xt because this distance is equal to 0, so there is nothing you have to do. And in case this distance is non-zero, then if by doing nothing, you don't get to the target, but somewhere away, this is really the distance, the gap that the control has to fill, right? Okay. So then given a system, if you give me, an initial datum, right? And a target, right? This is x0, and this is, this is x0, and this is the target xt. The size of the control you need is not really related to this distance, but is related to the distance between, the target and the point to which the trajectory reaches without any control. This is really the gap you need to fill with the control u, right? Okay, that's all. This is what the property tells you. And this is important to know, right? So, because sometimes our intuition is, oh, I have to, go from this point to this point. I should start acting immediately according to the distance. No. This is not the case, right? So it's like when you are taking the train. You take the train, you go from, say, Beijing to Shanghai. You take the train, you take the fast train. While you are in the fast train, there is nothing to be done, right? So here you are on the train. The train is taking you for free from this point to this point. So you don't need to work. The train is working for you. You are being driven to this point spontaneously. The only gap you have to fill is the gap from the train station to your home or to your office or to the restaurant where you have your appointment, right? So this is the gap. I mean, you could try to work this out from the very beginning, but this will not be very efficient, right? Because then all the, the energy that the train is putting to transport you for free, of course, free after you pay the ticket, right? You will have to do it yourself. Then you will have to walk from Beijing to Shanghai or take the bicycle from Beijing to Shanghai, and it will take a while. Okay, very good. Okay, and then there is another interesting property that, you see somehow in this particular case, we said there are examples of systems of very high dimension, right, which can be controlled by just one control, right? And I said, this is the particular case. You take an ODE of a very high dimension, maybe dimension order n, okay? And you can just control it with one control. So now, when you are in the general context, right, of general systems where you have U, which is just U1, UM, and the state X, which is X1 into Xn. So possibly many more components on the state than on the control. Why do you think that this is visible? Basically, the canonical decomposition of control systems, we could talk about this another day if you want, not really necessary for what I am planning to do immediately on the course, but this is important also that you keep that in mind. If M controls are able to control N components, is because each control Uj is somehow controlling Nj components of the system, and then the sum of these Nj's is equal to N. Okay, so this is just a very intuitive idea. You have N controls that are controlling all the components of the system, right? Is because, you know, each control is taking care of a number of components of the system, and that the union, right, and the union of all these components covers the full dimension of the system, right? That's a very natural condition. So you have, like, you know, you have just one control has to control all the components. If you have two controls, one control can control N1 components, the other one can control N2 components, right? And of course, in order for the system to be controllable, it is important that the superposition of N2 plus N1 is the full system, right? Okay. Now, you have probably heard also about Bang-Bang controls. Bang-Bang control is a very important notion, right? Why? Well, because you see, the controls we have built so far, right, are very nice and very smooth, right? They were given here by, the condition, the final characterization we got of the control was B star phi hat, and phi hat was the solution of the adjoint system out of the minimizer phi t hat of the functional J, right? So this is a very nice control. It's a very smooth function, right? So we say, well, being very smooth is very nice, right? From a mathematical perspective, I mean, smooth functions are beautiful, right? You can compute as many derivatives as you wish. In this context, they are even, analytic, because we are dealing with matrices, and, the exponential of a matrix depends analytically on this, say, multiplicative coefficients t. We have the power series actually representation of the exponential of a matrix. So everything is very nice. Now, being analytic is very nice from a conceptual mathematical perspective, but it's not so practical in applications, right? Because it means that if you were really the person to implement this control, you will have to be very, very careful, right? Because, the action you have to implement on the system is something so tricky, so smooth, but so varying, so much varying, so oscillatory, that you will have to really be very, very careful in order to be able to track this control, right? And as soon as you will lose attention a little bit, you will be out of the control, then you will miss the controllability of the system. So this is something that mathematically is very nice, But from a practical perspective, you know, if you are really the one to implement this control, you will say, well, listen, I would have preferred maybe a less nice, you know, trajectory for the control, path for the control, but simpler to implement, right? This is what the bank controls do, right? The bank controls, they have the property that a bank control is a control that is just taking two values. So it's some value plus m and some value minus m, right? How does a bank control look? Well, it's very simple. Sometimes it's m, sometimes it's minus m, sometimes it's m, sometimes it's minus m, sometimes it's m, some others is minus m, right? So this is precisely the concept of the switch, right? So what we do with the light in the office, we turn it on when it's dark, when turn it out when there is enough light coming from the outside. What does the thermostat do for the air conditioning? Well, it turns on when it's too hot inside, so we need cool air, but it turns off whenever the temperature is fresh enough. So that when, you know, even in the summer, if the temperature is cool outside, the air conditioning will not work. No needed. The outside temperature is anyhow 20 degrees, so you don't need air conditioning, right? So this is what we do in most, say, operational, practical, daily control systems we use. On and off, 0 and 1, bang and bang, right? M and minus M. You see, this kind of control system, you will say, well, but this is not even a continuous function. You will argue as a mathematician, you will say, I don't like this function. This function is not even continuous, right? This function is not even continuous. I don't like it. There is no limit. But from a control perspective, people will tell you, oh, this function is not continuous, but this function is very easy to implement in the practical application because the only thing you have to do is to switch on and off. So while you are minus m, you keep the system as it is. And then whenever the switching time arrives, you jump to m. Then you keep the control as m. And whenever the time arrives, you switch it off again to go to minus m. You keep the minus m until the next switching time arrives, and then you switch it on again, and then you have plus m. And in this way, you produce a bang control. Bang, bang, on, off. Okay, good. But you see, the controls I have written out of the, you know, minimization of the previous functional, in which you have an expression that was B star times phi hat, the distinguished solution of the adjoint system out of the minimization of the functional J. It was not bang bang. I said we got something that was very nice and smooth. Certainly not bang bang. So can I also, out of the Kalman-Rank condition, can I also produce bang bang controls? And the answer is yes. Yes, I can, right? Why? Because instead of minimizing, you see, before we have a minimization problem very naturally coming from Lax Milgram and the variational interpretation of the control problem. I had a functional in which I was integrating B star phi squared. Right? Now the square, I am putting it outside. Right? And I ask you, you know, I call this functional now JBB being for bang bang. Why? Because out of this functional, I will get bang bang controls. Why is that? Well, because you see, if you ask me, does this functional have a minimizer? I tell you, yes, it has. Why? Well, because this is a continuous and convex functional in the Euclidean space Rn. In order to minimize this functional, the only thing I need is this, say, quadratic quantity to be coercive. And this quadratic quantity is coercive, right? Because this quadratic quantity is an OR. And this is an OR because when I check what is missing for this seminode to be an OR, the only thing I need is that B star phi equals 0 implies that phi is equal to 0. But this is the unique continuation property I have checked. So you see that because of the Kalman-Rank condition and the interpretation of the Kalman-Rank condition in terms of the observability property for the adjoint system, this functional is coercive as well. And now when you write what is the Euler-Lagrange equation for the minimization of that functional, you compute the derivative and you see that, oh, out of this expression, right? So here it should be a phi, right? Out of this expression, what I see is that now the control is just this integral, which is a number, right? So this will be, you know, m, the amplitude of the bang control, and then I get it multiplied by the sign of B star phi hat, which is, you know the sign function, right? The sign function is just the function that is taking value 1 for the positive and minus 1 for the negative, right? Then it will be either plus 1 or minus 1. Plus 1 and minus 1 multiplied by m, it will give you a bang control jumping from minus m to plus m. Here there is an analytical comment to be made. People could say, oh, but you know, the sign function is 1 when the argument is positive, is minus 1 when the argument is negative, but it's not well defined when the argument is equal to 0. Oh, yes, that is true. But how many times B star phi hat will be equal to 0? Well, not that so many times, because phi hat B star phi hat can only be 0 on a finite number of points. Why? Because if it was 0 in an infinite number of points, right? Then because B star phi hat is analytic, it will be 0. And because of analytic unique continuation, phi hat will be equal to 0 because of the observability. So this will be a case where the minimizer of this functional, right, is 0. And when the minimizer of this functional is equal to 0, then it means that you are in the very lucky situation, right, in which in the absence of control, you drive the system spontaneously from the initial configuration to the destination without any effort. So you see that we are in a case where, you know, indeed, I can guarantee the system to be controllable of bang form. Okay? So now, assume, let me ask you something. Assume somebody tells you, okay, you got bang controls, right? Sometimes it's M, sometimes it's minus M. But somebody tells you, well, listen, but in our company, we use a very concrete actuator, right? And this actuator is not able to do M and minus M. It only does it for M equal to 1, right? So I have both this very simple actuator, and I cannot regulate the intensity, right? In order to implement this control, minus MM, I need an actuator that is smart in the sense that I can at least regulate the amplitude, right, of the jump from minus M to capital M. So here, right, I'm just taking M equal 1. I have an actuator which only does M equal 1. So what is your suggestion? If I really have to control a system that I know is controllable, but in which the actuator only does bang with M equal 1, 1 minus 1, 1 minus 1, 1 minus 1, what do you recommend me to do? How could I control a system in such a case when M is only allowed to be 1. Do you have any suggestion for this? Scale initial data. That's a good idea. So the idea of Cheche is that if, right, my experience is that, you know, I had a time window, 0 capital T, right? 0 capital T. And, you know, I experience the need of, you know, jumping from M into minus M and again and again and again. And now I have to do it with an control, which is just jumping from 1 to minus 1. Then what I can do is divide everything by M. The system is linear, right? So I can divide everything by M. So if I can control X0 with a control of size M, then I can control X0 over M with size 1. So this is one possibility, right? Good. That's excellent. It's a very natural idea. We are dealing with linear systems. The response of the system is linear. So what you can achieve with a control M, right? You can achieve it with a control 1, provided the initial perturbation to be controlled is M times smaller. This is just a matter of linear scaling, right? You can multiply the system and divide the system by constants. You keep, you know, basically the dynamics, you just see the scale, right? That's a very nice thing. Any other possibility? Assume I tell you, yes, but no, I'm sorry. I cannot scale X0, right? I don't need to control X0 over M. I really need to control X0, right? Because you see, scaling could be, I am moving from my apartment to a new apartment, right? And I need to move all my belongings, right? So I am not satisfied if I just move 10% of my belongings. I cannot do this, right? Because this will mean that I am not controlling fully X0. I am just controlling a percentage of X0. And I really need to control it all. So what is the other possibility I will have? What is the other possibility I will have? You see, there is something that is extremely important in control systems that, of course, then in every case, switch more times. That's a good idea, but what does it mean? That's a very good idea, Ma. But can I really switch more times? You see, for instance, if you are, I mean, this is, maybe I can switch to another app to write it better, right? Do you see now the keynote? I mean, the Blackboard? Can please someone confirm whether you see now a Blackboard in which I am writing? So we said the control is the integral from 0 to t of b star phi dt times the sine of b star phi. Right? So this is a number, and this is just the switching, plus or minus 1. Do you see these formulas I am drawing in the computer? Yes, okay, very good, thank you. Okay, but you see now, when is this switching? So the switching occurs in a number of time instances, right? In the time interval 0t, that I don't know exactly where they are, right? There are some switchings, but the switchings occur, I know that the switchings, right? So this is a switching time if b star phi tj is equal to 0, right? Because this is when precisely the sign is jumping from 1 to -1, from -1 to 1, right? And as I said, how many times does this switch? Well, this switches finally many times, right? Because phi is an analytic function, is the solution of the adjoint system, so maybe the minimizer, so, but it doesn't matter. Phi fulfills this adjoint equation. So phi switches finally many times. So you can think, for instance, on the particular case of the harmonic oscillator where phi is just this. And then phi is just a linear combination of exponential it plus beta exponential minus it. Or if you want to, you can write it down as cosine t plus b sine t. But you see that this is a function that is periodic of period 2 pi, right? Therefore, if you draw this function, what you see is something like this, right? And, you know, you have here just 2 pi in every period, right? And then in every interval of length 2 pi, you see you have 1 0, another 0, and another 0. You have 3 zeros in every time interval, 0 capital T, right? Then you see that you cannot fasten the zeros of the phi. Phi is the solution of the adjoint system. Anyhow, whatever you do, phi is always the solution of the adjoint system. So you cannot accelerate time on phi, right? In the way we are working, you cannot play with the time variable. I mean, if you will make you could accelerate time by maybe multiplying here by a constant, right? So then, yes, then, you know, this is like an acceleration of time, right? Because k times the derivative of respect to t, right, is like the derivative with respect to a new time variable s, where s is like t over k. So you are compressing time. But you are not allowed to do this, right? So the adjoint system is given. You cannot play with the time. So when you suggest, Ma, that I think it was Ma who said, well, if you want to, you know, if you want more zeros, then maybe you should accelerate the time, right? Sorry, I'm trying to get back to, okay. Here, right? I cannot really accelerate time. So what can I do? Well, what you can do, the idea was correct. You need more zeros, so you need a longer time interval, right? So if right, you need to control the system, right? If you need to control the system, but you are not allowed to, right? You are not allowed to jump from m to minus m, but just from 1 to minus 1, right? Then what you can do is to regulate the control time. Why? Because typically, this is something, of course, in every example you will have to check carefully. But what is the behavior you expect for the size of the control of a system? Of course, you expect that when the time is very short, if the time horizon is very short here, if you give me a very small time horizon and you tell me, oh, no, you have to really, you want to lose 5 kilos. And if you want to lose 5 kilos just in 1 week, okay, so you can eat nothing and then you have to run a marathon every day, right? If you tell me you have to lose 5 kilos during 1 year, then you say, okay, I take it easily. Of course, I have to do a diet, but I do it mildly. I take care of what I eat. And every day, maybe I do jogging for half an hour, and that's enough. So you see, depending on what is the time window you are given to control a process, you will need to control with more intensity or less intensity. So if the time window is very short, the control will go to infinity. If the time window is very long, the control will go down to 0. That's the principle. Okay? So therefore, now if you tell me, oh, you wanted the control to be of size 1, you said, you wanted the control to be of size 1, then I regulate. I say, okay, I take here m equal 1, right? So I take the maximal size of the control to be 1, and this means that I am computing a time for control which is t1. And this means in particular that if I need to switch more, as Ma suggested, what it actually means, I have to take a longer time horizon. Why? Because as I said, the solutions of the adjoint system, like in this harmonic oscillator, they just oscillate 3 zeros every 2 pi. Therefore, if I want more zeros, more switchings, I have to take longer time horizon, right? So then you have to keep that in mind, that because the Kalman run condition tells you that when a system is controllable in any time, you have to interpret that correctly, because that also means that in practical applications, you are allowed to choose the time of control. If you are allowed to choose the time of control, the control horizon, you will preserve the controllability property, but you will also regulate the amplitude of the controls. Okay, good, very good. Okay, so another important property of this adjoint methodology, I said there are several important properties on this adjoint methodology we are presenting here. One of them is that it's the full characterization of the control. And this is in agreement with the vision of Norbert Wiener. Control and communication go together. Actuators and sensors are both relevant parts of a control system. The second property was that the characterization of the control as minimizer of a functional is great because this allows you to build computational algorithms to compute the control, right? And the third remark is also very important, is that the control obtained by minimizing these functionals, they always are very distinguished, right? In particular, the control obtained by minimizing the original functional J is the control of minimal L2 norm, which is actually something which is extremely interesting, right? Because in practical applications, yes, of course, you want to go from x0 to xt, and there are many ways to do it, right? There are many ways you can do it. And then I will ask you, okay, now that you know that the system is controllable, you know there are many ways of controlling the system from one initial datum to one final destination. The question is, what is the one in which I am consuming less gasoline, right? What is the one that is optimal in the sense that the norm of the control I'm using is the least? And the point I'm making here is that the way we are building the controls is the one that guarantees that in the original case, the control is of minimal L2 norm. And in the case of bang control, the control is of minimal L infinity norm. Okay. Why is that? Well, you can do that simply by the following argument. You say, you recall the control, the control is doing this, right? The control is so that this duality is true. So wherever you take any other control, because this duality is always true, you will apply the Cauchy-Schwarz inequality, and you will easily get that the new control is less than the control of minimal norm. So when you use the fact that, you know, the control we are using is the one minimizing the functional, you have some extra property. And this extra property of being the minimizer of that functional, this Euler-Lagrange equation, allows you to show that any other possible control is less than the norm of this control just because of this Cauchy-Schwarz, in which, of course, out of which you can just drop one norm of U2 to get the norm of U2 less than the norm of U. And the same can be done in the context of bang controls, using that one of the controls we have is the one that is given by the Euler-Lagrange equation, and the other one is the general one. So this is another very important aspect, right? So then, you know, controlling, the conclusion is that controlling systems through the analysis of the adjoint, right, leads to several interesting conclusions, right? One, the first one is that, the first one is purely conceptual, right? Is that controllability is equivalent to observability, right? The second observation is that in this way we understand the Kalman rank condition. The third condition is that the control, we can build it computationally, right? Because, you know, we have a functional to be minimized out of which I can build the control. This is very nicely to be, you know, written computational. We will discuss tomorrow gradient descent algorithms. That's very classical, it's very simple, at least the foundations of the theory. Then there are, of course, many sophistications of that, in particular stochastic gradient methods apply in the context of machine learning and so on, among others. But the idea is very simple. As soon as you have such a duality characterization, this becomes something you can program in your computer, right? Other properties we have seen is that openness and density of the control property. You understand that, I mean, there are many systems that are controllable, right? And openness in particular is something very precious, right? Is what is called, you know, robustness, right? So in engineering control, you know, of course, experts, whenever you want to implement something, you want it to be robust, right? So you buy a new, you know, frigo or washing machine for your kitchen, you want it to be robust, right? You don't buy a washing machine that will work for 1 week and then it will be broken. You know, the computer, we need a computer that is robust. I need it for a few years, right? I don't want a computer so that tomorrow I cannot give my Zoom class, you know, in this Jilin University lecture series, right? Okay. And then the other property we have seen is that the amplitude to be regulated plane with the length of the time window, right? I can scale without modifying the initial datum. I can scale, of course, when I make the initial datum to be controlled smaller or bigger, but normally the initial datum to be controlled is not the one, I am not the one to choose. When you get to your office in the morning and it's 27 degrees inside, you don't choose that temperature, it's given, it's the initial datum, and you need air conditioning to cool it down. But of course, because the power of this, say, air conditioning system is given, you will need longer time when it's very hot. Then, you know, you can regulate the amplitude playing also with the length of the time window. And we can understand this also in the number of switchings of the adjoint system and the oscillations of the solutions of the adjoint system. Very good. And another property we have seen is that controls obtained are of minimal norm. And this is something also very important, right? Because, you know, the controls we obtain being of minimal norm, being that in practical applications, they are economical, right? They are performing very well. They are optimal, so there is no better you can do. Of course, as I have said, the optimality of the norm has to be interpreted in each case, right? In the corresponding setting, right? L2 in one case, and L infinity in the other, right? So in particular, you have seen that the control of minimal norm, right? Right? Of bang norm is minimal in L infinity. Why do you think this control is minimal in L infinity? Why, for instance, I could not expect that the control of minimal norm will be maybe oscillatory and smooth? Why do you think that the control of minimal norm has to be really bang and it will not have these smooth transitions? Why would you exclude these smooth transitions in the bang control? Well, the reason is the following. Assume someone claims that has a control of minimal norm and is smooth like this. I tell, well, this will not be of minimal norm. Why? Because you see, when you are doing this kind of transition, here in the middle, where you are not saturating the maximal and minimal constraint, I tell you, you are losing opportunities there. You see, what you are doing here with this control, which is smooth and going down, I tell you, you know, I could do it with a control, which will be bang, right? Basically, I will have the same area here, right? I will have the same area here with a control which has less norm, just by keeping it until the very time in which I have to jump. And if I will do this, then you see that I am moving from this upper bound on the control to this upper bound that is milder. So if, right, the control that you achieve is not bang, then is not of minimal L infinity norm, because it means that by this principle, you can compress its norm to the condition of enjoying further of the property of saturating the time some interval before you switch. That's the idea, right? And why it is about, you know, keeping the same integral here is because you see, when in order to build the bang controls, we were minimizing the integral of this absolute value. So the optimality condition is given really by not what is the amplitude or not how long you keep the control. It's just a balance. It's just this balance between amplitude and length of the time interval, area here of the action, the overall L1 norm of your action is the one that is determining the optimality. And it's that principle which tells, oh, L infinity optimal controls need to be bang bang. Okay, good. So once you have understood this idea, you can do many variants. And this, as I said, this is also very important in, in the context of machine learning, where, people say, well, we have seen Sivenko, right? Sivenko says, combining sigmoids, you can realize any function. So whatever, the data-driven system you are giving me, if I need to model, I can always build a model out of neural networks, right? Because neural networks can, realize any kind of complicated dynamics. That's fine. Yes, but people will always ask you, yeah, but I need, your neural network to be optimal in some sense, right? And that's normal, right? So people will say, please use as few layers as possible. Please use coefficients in your neural network that are smaller as possible, right? You want to realize your approximation property of neural networks with the least possible energy consumption. And this is precisely what we are doing here, right? There is a very important field in machine learning, right? Very important, yes. I mean, it's quite trendy actually, and it's very useful. It's called federated learning. Federated learning will be something like, two different groups of people cooperating in order to learn about something. You remember the problem I mentioned the other day, where I have these ways to be classified, plastic to yellow, paper to blue, right? And I was explaining you how I could build a neural network in order to do that automatically, right? Of course, in order to build this neural network, I have to work a lot a priori, because I have to understand how the coefficients of this neural network have to be cooked in order to be able to do that successfully, right? Federated learning is about two different groups of people cooperating with the same goal, right? So it could be like two different university hospitals trying to understand the same pathologies, right? Because they want to evolve faster. It could be, COVID epidemics, or it could be any kind of cancer or neurodegenerative sickness, right? So as soon as there is a big challenge, cooperation is like in the same as scientific publishing or scientific research, two groups, different universities, they, one is more, say, expert in the theoretical aspects, the other one is more expert in the computational aspects. They cooperate, and in this way, they can achieve more important goals and do it in a shorter time. So federated learning is about this, is how to do, the classical task of machine learning, like, for instance, supervised learning classification by the cooperation of two different groups. So here is the same, right? So this is the control formulation of this federated learning problem will be, in case I have a system, right? The system is the same as before, right? I have a system given by A. But now I have two different controllers, B1 and B2, right? Okay. Then the controllers are B1, B2. The two actuators are B1 and B2. And then I have two controllers, U1 and U2, right? So just to simplify ideas, now I have taken a system where, say, the dimension of the system is capital N. I'm sorry for the change of notation. So far was a small n, but it doesn't really matter, right? So this could be the original problem in which I am considering the temperature in the offices of the Faculty of Mathematics of the Jilin University. So this is a large vector with one value per office. But now I don't have just one, engine to regulate temperature. I have two of them, right? So I can play with two controllers, U1 with my left hand, U2 with my right hand. Each of them, is using a different compressor, a different engine, right, to generate and pump cool air into the system, U1 and U2. Okay, good. And then I ask you, could you please control the system in a switching manner? What does it mean, switching? It means that sometimes is the compressor B1 that is working, some other times is the compressor B2. But please don't use them both simultaneously, right? Okay, it's like, you know, if you are driving a car, you don't look to your cell phone, right? You either look to the WeChat or you drive, but you don't do two things simultaneously, right? So what about this question? So I let you think on this as an exercise, and we continue tomorrow morning, right? Solving this very simple exercise, and we will complete then the theory of finite-dimensional linear control systems, in which you already encounter some of the key ideas of the modern theory of machine learning, in particular about federated learning. Thank you all for your attention.